So, good evening, everyone. I welcome you all to the 10th live session of the NPTEL online course Basic Principles and Calculations in Chemical Engineering, course instructed by Professor S.K. Majumder from IIT Guwahati, and myself, Chaitra Borkar, a Ph.D. scholar from IIT Delhi, who will be conducting this live session today. So, some general information about these live sessions is that these sessions are conducted every week on Tuesday from 7 to 9 p.m. for the duration of this course. The recordings to these live sessions have been made available to you. The link has been shared with you, as well as you can access it through my YouTube channel. The structure of these sessions will be: firstly, we'll go through the overview of the lectures for the corresponding week, which is the week 10th this time, nearing almost the end of this course. And then we'll uh, solve some sample problems related to your assignment for this week. So let's get started. So week 10 started with lecture 29, which dealt with least square method linear equation fitting. So sometimes when we do some experiments, the experimental data needs to be expressed uh, based on the relation between the dependent and the independent variable. And we attempt to fit this experimental data in a mathematical form. It can be a linear form, it can be a parabolic form, it can be any mathematical form. So suppose there is a variable y, which is a function of many independent variables x0, x1, and so on. And the corresponding coefficient is b0, b1, and so on. Suppose also this can be a general variable, general expression for a variable. It can be a function of many independent variables. Suppose there is a linear relation that exists between the dependent and the independent variable, only one independent variable, and there is a dependent variable. So there exists a linear equation in this form: y is equal to b naught plus b1x. So these are the coefficients here. So you know this equation: y is equal to mx plus c. So here m is basically b1 and c is b naught. So these are the coefficients here. And suppose the experimental data given through this plot, I'll just zoom. So suppose these blue dots represent the experimental data for y versus x, and x is the our independent variable and y is dependent variable. Plus this straight line is the modeled linear fit. So suppose y depends on x in linearly. So this is the modeled line, which is given by small yi is equal to b naught plus b1 xi. And the error between these points for a corresponding xi. So at a particular xi, the error between the experimental data and the predicted model will be yi minus capital Y minus small yi. So this is the error. And in order to get the best fit, in order to get the best fit, we need to minimize the square sum of the square of the errors. So this is what is written here. So error is y minus y. We need to minimize f, which is the sum of the square of the error at each point. So all the errors. So this will be the error for this xi, the error for, sorry. So for if this is the xi, the error will be this distance. For this xi, the error will be this distance. So this is the just the error. We need to square it and then sum all these errors, sum all these values. So that is uh, the sum of the square of the errors, and we need to minimize that function. So in order to we minimize that function, and basically what it does is we need to compute, because at minima. So what are the unknowns here? We know yi, we know xi. We don't know b0 and b1. So df by d0 should be equal to 0 at minima, and df by db1 should also be 0. If we apply this to this function, to this function basically, so we get these equations, these two. These are the two equations that we get. And the rearrangement gives us this. So summation of 1 to n of b naught is basically n b naught. And we can take this b1 out because it's a constant. So b1 is taken out. And same the rearrangement for these equations. So basically we get these two equations. Equation 1 and 2. So these two equations are, if you can see, if we have a number of points, suppose this is yi, this is xi. So suppose we have a number of points, suppose 0, 3, 5, 8, 10, suppose, and xi will be some value, suppose uh, let it be 1, 4, sorry, 1, 4, 10, 15, 18. So these are the values we know. So whatever the experimental data, so we know yi, we know xi. So summation of that will be a number itself. Okay. And summation of this yi will also be a number. N will also be a number which is number of data points. And the same goes for here as well. Xi square will be, we square each of these point and then sum it. And xi will be the multiplication of this and then sum it. So these are basically this is the set of linear equations of the two unknowns. So we have two unknowns b naught and bi, and we have two equations, two linear equations. So we can solve it to get the value of b naught and b1. That is what is written here. So this is, if you can see, this is summation yi into summation of xi square. So you need to firstly square the xi, then sum it, and then multiply it with yi. This is what the term is. Then minus summation yi into whole square of summation xi. So this is different from this. This is not equal to. For some cases, it may be equal. I'm not discussing that here. But for this, in a general case, this is generally not equal. So what you do here is you square the xi beforehand, each of these xi, and then sum them. Here you get the sum of xi and then square it, which is basically not equal to this. So keep that in mind. And then in denominator n into summation xi square minus summation xi whole square. And then we get the expression for BA1 as well. To determine the goodness of the fit, if your model which you have predicted, it is the best fit for your experimental data. Suppose this is your experimental data. If suppose this line is the best fit for your model, how do you gauge that is using the correlation coefficient, which is given here by r square. So and the expression is ss xy whole square upon ss xx into ss yy. And the relations for these are given here. So ss xx is basically the difference between each data, each xi minus the mean. This is mean. X bar is mean, whole square of that and their summation. And the same goes for SSYY, which is mean of y, y bar, which is mean of y. And SSXY will be the multiplication, which is the interaction. So xi minus x bar into yi minus y bar and summation of that. And this r square, the range is between 0 and 1, and r square tending to 1. If it is nearby 1, suppose 0.999, it reflects a better fit. In the least square method linear equation fitting, we then saw the fitting of non-linear equations by converting them in linear form. So suppose there is y is equal to ax square plus b. You can convert this to y is equal to x by b by assuming that small y is equal to capital Y. That's okay, and x square is equal to x. So you basically assume that this x square is another variable capital X. The same goes for the next one. Y square you assume as y, and then 1 by x you can assume as x. One more here is y is equal to a into x to power b. So you take logarithm on both sides so as to remove this multiplication as well as the power. So ln y is equal to b ln x plus ln a. So b will be your slope and ln a will be your intercept, and then you can find out whatever the intercept is will be e to the power. So a will be um, exponential of the intercept basically, and same goes for b. And you can convert these other functions as well using these relations. Lecture 30 dealt with non-linear algebraic equation system. Non-linear independent A set of non-linear independent equations is given here. So this is fx, which has a number of functions which are dependent on f1 to fn, which are dependent on the variables x1 to xn. So the methods to solve them are numerous, which are given here. Successive substitution, these were mentioned. Differential homotopy, this was mentioned. Newton method, Newton-Raphson was discussed. Regular falsy method, this was mentioned. Spreadsheet solution method was discussed, and graphical solution. So we look at the Newton's method here, which originated from Taylor series expansion, and the basic formula for the Newton's method is given here. And this is basically an iterative method. So suppose you need to find the solution of a function given here by this curve. This is a function, and you need to find its root. So what will be its root? Where it cuts the x-axis. So this is its root, and you need to find that root. So what you do is you take an initial guess. So this will be your initial guess x naught, and you go from x naught to x1 to x2 to xn using this formula. So suppose x1 will be x naught minus fx naught upon f dash x naught. So the Newton's method is shown here graphically as well. Sorry. So suppose this is the initial guess x naught and fx naught. You draw a tangent from here. It leads you to the x1. Again, at this point, x1 comma fx1, you draw a tangent. It leads you to x2, and you do it successively, and you reach a point where the tangent uh, touches the curve intersecting at x-axis. So that is your solution. Then this was for a single equation. Then solving a set of nonlinear algebraic equations, you get this formula from the Newton scheme. Is that x at kth iteration is equal to x at k minus 1th iteration minus Jacobian of this set of nonlinear algebraic equations into this whole set. Inverse of Jacobian into this whole set. So what is Jacobian is shown here. Yeah. So suppose these f1, f2, fn are function of x1 to xn. So what will be the Jacobian is? that firstly the f1 will be differentiated in the first row is the differentiation of f1. Each element is differentiation of h1 with each of these variables. So df1 by dx1, df1 by dx2 till df1 by dx dou xn. And then why dou? Because it is a function of other variables as well. So partial differential. And the same, the next line will be the partial differentiation of the function f2 with each of these variables, and so on till xn, fn until xn. So suppose we have two functions. Sorry, suppose we have two functions. Uh, f1 function of x1 comma x2 is equal to x1 square plus x1 x2 minus 10, and f2 is also a function of x1 comma x2, uh, x2 plus 3x1 x2 square minus suppose 37. So what will be the Jacobian of this system of equation is that dou f1 by dou x1, dou f1 by dou x2, because there are only two variable x1, independent variable x1 and x2. Then dou f2 by dou x1 into dou f2 by dou x2. So this is the Jacobian, which will be equal to what will be dou f1 by dou x1 here. So this is x1, and you need to only differentiate with respect to x1 only. So sorry, this is x1 square. So this will be 2x1 plus x2, because x1 square differentiation is 2x1, and x1 here the difference x1 x2 the differentiation will be, because this is x1, so differentiation will be 1 into x2, so x2, and 10 is a constant, so no value here. And then dou f1 by dou x2. So we need to keep x1 constant and x2 variable. So x1 square will be 0, x1 into x2 will be only x1. And then next we have dou f2 by dou x1. So dou f2 by dou x1 will be with respect to x1. So this will be 0. This will be 3x square. 3x2 square, sorry. And then this is again 0. Next, dou f2 by dou x2. So that will be, we have to keep x1 constant. So x2 will be 1, differentiation of that with respect to x2. And then x1 is constant, so 6 x1 x2. So this is your Jacobian for this set of equations. So we have two independent variables and two equations. And you can compute Jacobian at a particular point. Suppose you need Jacobian at 6, comma 1. So you need to put x1 here as 6 and x2 here as 1. So you can compute that and take the inverse of that, and then whatever will the fx. So fx is these. So fx is basically f1 x1 comma x2 and f2 x1 comma x2. This is your fx. So yeah. So now we move on to lecture 31, which dealt with numerical integration. So whenever there is no definition of the function available, you can, and only fx at different values of x is given. So this is your y is equal to fx. Suppose this is a curve, y is equal to fx, and you don't know what this the mathematical expression of this curve is. You only know this value of fx at different x's. So how to compute the area under the curve? So you can use two ways, which is the trapezoidal rule or the Simpson's rule. So for equal intervals, the trapezoidal rule, the area under the curve is using the trapezoidal rule is given here, h by 2 into f1 plus fn. So f1 is f at x1 first. So there will be data point. Suppose f1 is f at x1. Okay, this is x1, and then fn will be f at xn, and so on. So plus twice into summation of fi from I2 to n minus 1. So this is the representation for the trapezoidal rule is that you divide the range of x1 to xn into a number of data points, and basically these are the trapezoids that you are creating, and the summation of the area of these trapezoids will give you the area under the curve. And here h is basically xn minus x1 upon n, which is n is the number of intervals. So these are the data points a to b. Okay, uh, number of data points is x to x0. If you count this as x0, and this is as xn. So these are the data points. What are the number of intervals is this? This is the number of intervals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the number of intervals, and number of data points are these points. Okay, that's the difference between the two. And the Simpson's rule states that it is applied for only odd number of equally spaced data points. Equally spaced data points. So the distance between this and this is equal, this and this is equal. All of these distances are equal. And the data point should be odd number. So if the data points are odd number, so suppose there is 0 to 4, and we have 1, 2, and 3. So number of data points are 0, 1, 2, 3, 4, 5. Okay. What are the number of intervals? Number of intervals is 1, 2, 3, 4. So number of intervals is 4. So for odd number of data points, number of intervals will be, what will it be? It will be even. Okay. Number of intervals, or the terminology can be sub-intervals. So the area under the curve is given using the Simpson's rule is s by 2 into f1 plus fn plus 4 into fi, which has all the even data points, even number of data points. Okay, plus 2 into fi, all the odd number of data points till n minus 2, and this is till n minus 1. And in the Simpson's rule, there's a difference. Is that it it assumes each of these 3-point section is a parabola. So this is first section, this is the second section, and this will be the last section. So it assumes that these are the parabola, and it computes the area under the curve in that manner, and then sums it. So we start with the assignment questions basically related to your assignment. Um, the first question is the coefficients, just a minute. Yeah. So the first question is the coefficients of linear fit model using least square method is derived from differentiating the sum of errors with respect to the coefficients. So it's saying sum of yi minus yi. If you this is some function, and if you differentiate that with respect to these coefficients, you get the coefficients basically. Uh, if you equate it to 0. So, is that true or false? As we have already discussed, this is a false statement because we need to square this. This is only sum of errors. No. Sum of squares, sum of the square of errors. That is what we need to do. So, this is incorrect. It's a false statement. Next question. In Newton's method, if xi is equal to xi plus 1, then fxi by f dash xi is greater than 1, fxi by f dash xi is less than 1, fxi by f dash xi is equal to 1, or fxi by f dash xi is equal to 0. What will be the correct statement here? What will be the correct answer here? So we know from the Newton's method is that xi plus 1 is equal to xi minus fxi upon f dash xi. So if this is equal to this, so this should be equal to 0. So D part. Next question, find the root of uh, this function sin x minus exponential to the power x. Using Newton's method, take x naught minus 4. So, as I've discussed already with you, whatever these iterative methods are, you need to have some initial guess for that. So, here that's what is given to us. So, there is some function, we are given sin x to the power e to the power 1x using Newton's method. So, we know x naught beforehand, we minus 4, or we could have assumed it. How to assume that x naught is firstly, suppose there is a function, not this function, any function. So this is some function. So you need to have some interval where the function changes its sign. So fx is positive in this range and negative in this range. So when it changes its sign, you need to have that range. So you need to keep on computing your fx and assuming some values to get this range, and then take either this or this point as your x naught. So for the Newton's method, basically, if you are basically close to your solution, if you take the initial guess close to your solution, the iterations are basically less and it becomes faster. The computation becomes faster. So x naught is minus 4. So we know what will our x1 be? X naught minus fx naught upon f dash x naught. So what is f dash x? Only f dash. This is fx. So what will be f dash x? So that will be cos x minus e to the power x only. Okay. So x1 will be minus 4 minus sine of minus 4 e to the power minus 4 upon cos of minus 4 e to the power minus 4. So you compute this using calculator, right? So calculator, keep in mind that calculator setting to be in radians. Okay, because this is a radian value. So we do that. We compute this x1 here. So we get x1 as minus 2.9. Okay. Next, what will be x2? So it will be minus 2.9 minus, again, sine of minus 2.9 e to the power minus 2.9 upon cos into minus 2.9 into minus e to the power minus 2.9. So you get that. So you get x2 as minus 3.1867. Okay. For next iteration, you need to put, again, this will have x2. So minus, again, the same thing. Minus f of 3.18 minus 3.1867 upon f dash of minus 3.1867, and then so on. So x3 will be minus 3.183. Then x4, again, you keep this minus 3.183, sorry. So you also get x4 as minus 3.183, and you see that x3 and x4 are identical. Again, you go for, again, x5. You see what happens is, again, minus 3.183. So as we had seen that xi is equal to xy, xi plus 1 is equal to xi. So this is xi plus 1, this is equal to xi. So that means fx upon f dash, fxi upon f dash xi is equal to 0. So that means fxi is equal to 0. So your root comes out to be this minus 3.183. You can check that as well. So f of minus 3.183 this comes out to be a very small value. It's minus 6.56 into 10 to power minus 5. It comes out to be a very small value. So yeah, you can say that this is the root. Next question. Calculate the integral value of the equation, this equation, y is equal to x into fx dx from 2 to 5 using trapezoidal rule and the data given below. So this is the data given to us, x and fx. So we don't know what will be the integral, what will be the mathematical relation of this x into fx. So basically you multiply this x into fx. So you can multiply these values. So 2 into 3.81. So this will be 7.62. Sorry. This 2.5 into 1.8 is 4.5. 3 into 0.88, sorry, will be 2.64. 3.5 into 0.57, it will be 1.995. 4 into 0.06, sorry, 4 into, sorry, 4 into 0.66 is 2.64. Then 4.5 into 1 is 4.5 again. And then 5 into 1.53, it gives us 7.65. So this is your x into fx. So you need to compute the integral value of this equation using the trapezoidal rule. So trapezoidal rule states that from 2 to 5 we are given. So it will be, this is 2 to 5. So value of x from 2 to 5. So this will be h by 2 f1. So you need to compute what is the, how many number of points are there. So number of points is 1, 2, 3, 4, 5, 6, 7. And the interval you can also get it. So h is xn minus x1 by n. Number of data points given to us are 7. Uh, this n is not number of data points, it is number of intervals. So if the number of data points are odd, number of intervals will be even and less than 1. So that will be n minus 1 basically. Number of data points I can write as n number of data points, and capital N will be small n will be n minus 1, which is number of intervals. So we know number of intervals is 6. So 5 minus 2 upon 6. So 3 by 6. We get 0.5. H as 0.5. Okay. So we get that, and then this will be F1, F2, F3, F4, F5, F6, F7. So this will be F7 plus twice of F2 plus F3 plus F4 plus F5 plus F6. So we need to compute that. Uh, so F1 will basically be 7.62. F7 will be 7.65. So H is given to us as 0.5 by 2. F1 is 7.62 plus 7.65 plus twice of F2 is 4.5 plus 2.64 plus 1.995 plus 2.64 again plus 4.5. We get the value as 11.955. There is some issue here. It will be, this is close by. This will be 11.955. Calculate the area under the curve for y is equal to 0 to 1 x cube into dx for n to n4 using trapezoidal rule. So n here is again number of subintervals. Okay. So
What is the solution of last question? Can you please repeat that?
11.955. You need
Okay.
the explanation or just the solution?
Ma'am, just solution. I got that.
You got the 11.955?
Yes, ma'am.
Were you calculating alongside me?
Yes, ma'am.
Okay. Next question. Calculate the area under the curve for y is equal to 0 to 1 x cube dx for again number of intervals equal to 4 using trapezoidal rule. So now here we are not given the data points. However, we know what the equation is, but we need to compute it using the trapezoidal rule. So you can write x is the number of subintervals is 4 from 0 to 1. 1 minus 0 by 4, you get the h. So 1 by 4 is 0.25. So The width will be for each data point will be 0.25. So x is 0, 0.25, 1, oh, sorry, not 1, 0, 0.25, 0.5, 0.75, and 1. So number of data points is 1, 2, 3, 4, 5 again. Now fx at these points will be 0. X cube of 0 is 0 only. Then fx at 0.25 will be 0.25 cube basically. So that is 0.015625. Okay. Uh, then zero point 0.5 cube will be 0.125. Sorry. Sorry again. Then 0.75 cube will be 0.421875. And then 1 cube will be 1 only. So I'm keeping these so many significant numbers is that to get the exact answer basically. So you can either truncate it to 3 significant figures. Usually people keep it up till 3 significant figures. So this is x and fx. So we need to compute using the trapezoidal rule. So again, the area will be h by 2. So h is again 0.25 by 2 into f1 is 0 plus f final fn or f in this case f5 is 1, then twice into 0.015625 plus 0.125 and plus 0.421875. Okay. You compute that value. So the answer comes out to be 0.2656. Okay. Next question. Use trapezoidal method to compute y is equal to from the limit 1 to 2 1 by x square dx for n2. Okay. So 2 are the number of subintervals. So again 2 minus 1 by 2 we get 0.5. So it's basically x is 1, 1.5, and 2, and fx will be 1 by x square. So 1 by 1 square is 1 only. 1 by 1.5 square is 0.444. And then 1 by 2 square is 0.25. It's not many number of data points here. So what is the area under the curve? And we need to only compute using the trapezoidal rule. So h we are given as 0.5 by 2 into f1 is again 1, f final is 0.25, f you can say, and then 2 into 0.44. Quite easy. So the answer comes out to be 15345. It's given 5347. It's 5345. Compute the approximate area under the curve for the given data using Simpson's rule. So now we are given fx at different x, and you need to compute the area under the curve using the Simpson's rule. So what will be the area for this given limit -4 to 8? So this is again -4 to 8 fx dx. That will be you need to compute h again. So number of data points is 1, 2, 3, 4, 5, 6, 7. Number of data points. You can apply Simpson's rule. And number of intervals will be 7 minus 1, 6. 8 minus 4 by 6. This is your h. Sorry, 8 plus 4, because this is -4 itself. So 8 plus 4, 12 by 6, you get 2. And that is what the interval is. From -4 to -2, the interval is 2. From -2 to 0, the interval is 2. From 0 to 2, the interval is 2, and so on. So this is your interval or width. So I write the relation here, h by 3 into, sorry, f1. So this is f1, this is f2, f3, f4, f5, f6, f7. I can write it here. f1, f2, f3, f4, f5, f6, f7. Okay. So f1 plus f7 plus 4 into all the even points. So f2 plus f4 plus f6 basically, and then 2 into f3 plus f5. So this will be the relation. So h is not 0.2, it's 2 by 3 into f1 is 2, f7 is 13 plus 4 into f2 is 4, f4 is 7, f6 is 12, okay, plus 2 into f3 is given as 6 plus f5 is 9. We need to compute this value quite easy. .33 is the answer. For Simpson's rule to be applicable, the number of subintervals should be odd. What will be the correct answer here? Is it true or is it false? As I've discussed with you, the number of data points should be odd, not the number of subintervals. So suppose there are number of data points x 0, 2, 4, 6, 8. So these are 5 data points, but the number of interval is 1, 2, 3, 4. So capital N is 5, small n is 5 minus 1, 4. Okay. So number of, for the Simpson's rule to be applicable, we know that the number of data points should be odd and they must be equidistant, obviously, and the number of some intervals should be obviously then even. So this is a false statement. Next question. The trapezoidal method will give more accurate result if the number of subintervals are increased, number of subintervals are decreased, the width between the data points is increased, and none of the above. So suppose there is a function and you assume, and this is basically the width between the data points. Okay. So you basically assume some trapezoids. Okay. So this is your trapezoid. And again, this is your trapezoid. So there may be, because this is an approximation, so the it may not give you the accurate result. Plus, if you keep on decreasing, suppose this is the number of data points which is quite less right now. If you increase the number of data points, so you get a better approximation. You get near to the accurate result. So you need to increase data points, or you need to decrease the width or subintervals. So this is incorrect. Again, this is incorrect. The correct answer is B part. Okay. Oh, sorry, this is written number of subintervals. Sorry, sorry. So number of sub. So width should be decreased again. Increase data points or increase number of subintervals. Sorry, my bad. So increase number of subintervals. So this is again incorrect. This is the correct answer. A part. Next question. The Newton's method is based on Taylor's series. Is this true or false? As you have seen in the overview itself, yes, it is derived or it can be derived from Taylor series. This is the true statement. Because suppose fx around x1, you can write this as fx1 plus x minus x1 f dash of x1. This is the truncation of Taylor series till the two terms only. So using the Taylor series, you can write that. And suppose if you keep fx is equal to 0, so you get fx1 is equal to minus of x minus x1 f dash x1. So f dash fx1 by f dash x1, you basically rearrange it. So x is equal to x1 minus of fx1 by f dash x1. So that's what you get. So yeah, this is true. Next question. The root of a continuous function fx lies between a option A -1 between -1 and -2. If the fx is between -1 and -2, the x is between 1 and 2, fx is between minus 1 and 1, or x is between minus 1 and 1. So we are not given any information about x. So we we assume the function it has a root. If we assume the function has a root, so suppose this is some function. Okay, so this is this is the root of that function. This is fx, and this x, some x is the root. Okay, so basically the fx should lie between minus 1 and 1. I told you that the sign of the fx should change that range. So the sign of fx is changing here. It is not changing here. So these two are irrelevant because we are not given any data for x. So most appropriate will be these two options and to choose from. And then the correct will be C part. So fx may be suppose, sorry, fx will be suppose this is minus 1 and this is 1. So it is changing sign. Okay. Next question. The Newton-Raphson method can be applied to compute the roots of those functions for which f dash x is undefined at x. This is a false statement. It cannot be applied because you need to have that f dash x at that x defined. Okay, if it is undefined, you cannot compute the next iteration. Okay, false statement. Compute the area under the curve for y is equal to limit 0 to pi by 2 integration of cos x dx for nx. N is again number of subintervals here. So pi by 2 minus 0 by 6. So basically pi by 12. Okay, this is the h. Again, these are values in radians. So set your calculator to radian. Radian mode. Okay. So x is given to us 0, pi by 12, pi by 12 plus pi by 12 will be 2 pi by 12, so pi by 6. Pi by 6 plus pi by 12 will be pi by 4. Okay, pi by 4 plus pi by 12 will be pi by 3. Then pi by 3 plus pi by 12 will be 5 pi by 12. And then 5 pi by 12 plus pi by 12 will be pi by 2. You need to compute the fx at this point. So fx cos of 0 is 1. Cos of pi by 12 will be 0.9659. Okay. Then cos pi by 6, 0.866. then cos pi by 4, 1707, then cos pi by 3, cos pi by 3 is 0.5, then 5 pi by 12, 0.2588, and cos pi by 2 is 0. So we need to compute. We are not given any method here. So number of data points is 0, 1, 2, 3, 4, 5, 6. We can either apply Simpson or trapezoidal rule. I'm applying Simpson's rule. So h is given to us. So this is h 5 by 12 by 3 into f1 is 1, fn or f7 you can say 0, 1, 2, 3, 4, 5, 6. So f7 is 0 plus 4 times f2, f4 and f6. So and 9659 plus 0.707 plus 0.2588 plus 2 into 0.866. This is F3 and this is F5 plus 0.5. So what is the answer that you get? It roughly comes out to be, sorry, 0.9991. That's what your answer is. So if you see, so this is your area under the curve, which is equal to 1. Okay, this is 0, this is pi by 2, this is 1, and this is your area under the curve, which is, this is the cos x. Okay, the trapezoidal method will give exact area if the function to be integrated is parabolic in each interval. Is this true or a false statement? This is a false statement because the trapezoidal method, suppose in each interval, if this comes out to be a linear one, because suppose this is a section of this curve and you need, and this is the interval. Let's suppose if you zoom in a section of a curve, Suppose this is the curve and you zoom in this section and this is the interval basically. So you are basically calculating this area, but the area that needs to be calculated between this interval is this. So you are underestimating the area. Okay. So if it is linear, if all the intervals are linear, the curves in all the intervals are linear, then you'll get the exact answer. So this is a false statement. It should not be parabolic, it should be linear. Next question, the Simpson's rule is applicable for equidistant even number of data points and odd number of subintervals, equidistant odd number of data points and even number of subintervals, any number of equidistant data points and subintervals, any number of data points and subintervals. They may be equidistant or not. So what is the correct answer here? As we have discussed, the number of data points should be odd and the number of subintervals or intervals, you can say subintervals. So n odd and small m, which will be or n capital amalgam, so it will be basically even. So B part is the correct answer, and they should be equidistant. Next question: compute the solution of this function x plus log x for x naught 0.6. So you have to use the Newton's method. So we are given x plus log x. So what will be the f dash x? So f dash x will be 1 plus 1 by x. Okay. So x naught we are given. So x1 will be 0.6 minus fx. So fx is point sorry 0.6 plus log of 0.6 upon 1 plus 1 by 0.6. So we compute that. This should be this is, you can say, log e. Okay. So ln. So your x1 comes out to be 0.5665. Now x2 will be 0.5665 minus f of 0.5665 upon f dash of 0.5665. Okay, so that will come out to be 0.5671. Again, x2 will be 0.5671 minus f of 0.5671 upon f dash of 0.5671. So this comes out to be 0.5671 again. Then x3 again 0.5671. So we have stumbled upon the root for this function. So this is the answer. The approximate value of the integral y is equal to 0 to 2 1 by 1 plus x dx for n is equal to 4 using trapezoidal rule is, so we are given x, so we are given a number of subintervals, and 2 minus, sorry, h is 2 minus 0 by 4, so 2 by 4 is 0.5. So we are given x between 0 and 2, so 0, 0.5, 1, 1.5, and 2. So number of intervals 1, 2, 3, 4. And number of data points is 1, 2, 3, 4, 5. So if you count these lines, these are basically number of intervals. 4 lines, 4 intervals. Don't count these lines, okay? Only these lines between 0 and 2. So, and fx is 1 by 1 plus x. So we need to compute that. 1 by 1 will be 1 only. 1 by 1.5, we get 0.667. 1 by 2 will be 0.5. 1 by 2.5, we get 0.4. And 2 by, sorry, no, 1 by t, we get 0.33. So this is a decreasing function, you can see. And then you need to compute using the trapezoidal rule. So area will be 0.5 by 2 into f1 is 1 and f final or f5 is 0.333 plus 2 into 0.667 plus 0.5 plus 0.4, then that's it. You need to compute the value using the calculator. 1 plus 0.333 plus 2 into 0.667 plus 0.5 plus 0.4, 1.11675. This is the value. Yeah. Next question, I guess the last question for today. The approximate value of the integral y from 0 to 4 x by fx dx for the given data and n is equal to 4 using the Simpson rule is, so x by fx we need to compute. So you compute it here. So this will be 0, this will be 1 by 6, or you can write 1 by 6 as 11667. 1167, then 2 by 10 will be 0.2, 3 by 13, again an irrational number, I guess, 1230. 2307, so 231 you can write. Then 4 by 18, so 0.2222. So point. So this is your x by fx. So you need to compute the area between 0 and 4 and n is 4. So you need to compute first the h. So 4 minus 0 by 4, so h is 1. Again, you can see the width is 1 only, 0 to 1, 1 to 2, 1, 2 to 3, 3 to 4. So yeah, h is 1 by 3 into f1 is 0, f final is 0.222, then 4 into the even values, values at even data points, number of data points, so 0.167, and then this is point two, sorry, 231 plus 2 into 0.2, cover all the data points basically. You need to compute the value again. 738, 737, 738 nearby. Yeah. So that's it for today. Any further questions, anybody? Any questions? If there are no further questions, I'll go ahead and close the session for today. Thank you everybody for joining.